Here we're continuing with problem 24 in the AP Physics textbook in Chapter 2. So this is probably the most difficult part of the problem. You're supposed to write an equation for x as a function of time for each phase of the motion. So from 0 to a, and from a to b, and from b to c. So we are actually going to use the second kinematic to help us out with this problem. Remember the second kinematic? Is this. So let's do from 0 to a. Just plug things in here. So we're looking for xf, and let's just call that x1 for the first interval. Our initial position is 0. You can see that just by the graph, and we can assume that. Our initial speed is also 0, so we can just get rid of that term. And then we calculated our acceleration before when we made our acceleration time graphs. So remember, we calculated it to be 3.3. So it's going to be 1/2 times 3.3 times t squared, which ends up being 1.67 t squared. Pretty easy. Okay, now from a to b, again, we're going to just plug things in to this formula. However, remember that time means time interval, so the time interval, or the change in time, so the change in time is going to be whatever time minus 15, because that's where the interval a starts, at t equals 15. So instead of writing t, we need to write t minus 15. Okay, so for AB, we're going to call this x2 for second interval. So we have, we know that this time it starts out at position 375. We calculated that from this triangle here. So xi is going to be 375. And then we know our initial speed at that point is 50. We can just tell that by the graph. Remember, we've got to write t minus 15. We also know during this interval that the acceleration is 0 because this line is flat, so we can just drop the last term of the second kinematic equation. So, if you solve this out, you'll get 375 plus 50t minus 750, and you'll get a final answer for that part of 50t minus 375. All right, now we've got BC, which involves some algebra, or some more complicated algebra. So we'll call this x3 for third interval. And this time, our initial position is going to be the total distance traveled by these first two intervals. And if we recall from part A of the problem, the first two intervals were 375 and 1250. So again, this is just my initial position, xi, in this formula. My initial speed is going to be 50. And then again, t t refers to the change in time. So for this interval, it's going to be whatever time minus 40, because that's where the interval starts at t equals 40 seconds. So we're going to have times 50 t minus 40. And then again, from a previous part of the problem, we calculated that the acceleration of that last interval was negative 5 meters per second squared. So for the a in our second kinematic, we can plug in negative 5. And remember, we still want to plug in for time, the time interval, so t minus 40 again. And that gets squared. So let's move through this problem. So we've got x3, just adding these two together, you get 1,625. Then you get plus 50t, so just distributing the 50. And then I'm just going to divide the negative 5 by 2. And then I'm going to FOIL this out. And I can pretty much do that in your head. So you'll end up with t squared minus 80t plus 1,600. Okay, now let's start combining like terms. So we'll do this number and this number. And that gets us negative 375. Now let's distribute this negative 2.5. Okay, continue to combine like terms. So there's no other term with the t squared. And then negative, let's do the t's, plus 250t. And then these numbers. So you get negative 4,375. Whew, so that was a really big part of that problem. However, E is really easy. E asks us what is the average velocity of the car for the entire interval. So for that, we just want to use that ninth grade equation, V equals d over t. So d we had actually calculated in the first part of the problem. It was that 1875 meters. And it travels for a total of 50 seconds. So if you just divide those numbers, you end up getting 37.5 meters per second.